What is a motherboard? Motherboard? Like when she tells that story that I've heard like 100 times about when I was young and crayon up the nose. And man, I just wish she'd stop telling that story. Ha! That's a joke. No, where the CPU or the central processing unit is colloquially referred to as the brain of a PC, the motherboard or the main board is often described as the backbone. It's the component in a PC, and for that matter, pretty much any other electronic device, whether it's a game console, CE device, a piece of industrial equipment, or a cell phone, that contains all the slots that everything else goes into. All right, so how do I find it? Well, that's usually pretty easy because it's the largest PCB or printed circuit board inside the device, and it's covered in slots, connectors, chips, and other electronic doodads. At its very core, a motherboard is just a bare PCB and contains no actual processing power. It relies on other processors like the CPU and GPU, which are sometimes socketed in and at other times soldered on directly to perform all of the actual work and give life to your device. But that doesn't make it simple. Motherboard designers are tasked not with creating a simple platform onto which everything else will be stuck like Lego, but rather with crafting an infrastructure for some of the fastest and most delicate electronics imaginable. Even though the majority of the other components used in the system aren't manufactured by the motherboard maker, they are responsible often for choosing these components for their placement and configuration and making sure that every signal will be sent where it's needed, interpreted correctly, then passed to where it needs to go, and all of this without excess interference. Even something as seemingly trivial as a single trace that's a little bit too long can cause one electrical signal to be a little bit late and another a little bit early and cause instability. That's why you'll sometimes see little zigzag patterns in the traces on a PCB. Those aren't for beauty, they're not for looks. Everything about a motherboard is highly functional. A motherboard also isn't purely hardware either. There's a software or firmware component. On a PC, this is referred to as a BIOS or UEFI, and is often the difference between a good motherboard and a great motherboard. This software acts as a way for the manufacturer to correct small bugs that are inevitable with something so complex, and to add functionality in the future. It also serves as a way for the user to alter settings or tweak them for optimal functionality. On consumer electronics, this software component also exists, but it's normally not user accessible. Alright, so what if my motherboard dies, which might even be why you're sitting here watching this video? Well, for consumer electronics and phones and whatnot, you're often hooped. If you can find a new one, there are often extremely fragile cables and connectors attached to them, and if you can't find a detailed guide on a site like iFixit, for example, I would recommend leaving it to the pros. For a PC, life is a bit simpler. Many PCs use industry standard components, including the motherboard, but many others use proprietary and expensive alternatives. So the only way to find out for sure is to contact your manufacturer directly, but there's a good chance that you'll be able to get your hands on something. Once you've got a new one, replacing a PC motherboard is, in many cases, not difficult, but it can be time-consuming and tedious, and will usually involve removing pretty much every other component in the system in order to extract it and replace it.
You have big ideas to streamline your business and drive sales through the roof. But to get there, your ideas need business apps. And business apps have always been too expensive, especially in times like these. Behind each one is a world of complexity. They need a data center with office space, power, cooling, bandwidth, networks, servers, and storage. A complicated software stack, and a team of experts to install, configure, and run them. You need development, testing, staging, production, and failover environments. And when there's a problem, good luck. You call technical support, and they don't know, so they blame someone else. Oh, and when new versions come out, you would upgrade, but that might bring the whole system down. Now, this is for one app. When you multiply these headaches across dozens or hundreds of apps, it's easy to see why the biggest companies with the best IT departments aren't getting the apps they need. Small businesses don't have a chance. Cloud computing is a better way to run your business. Instead of running your apps yourself, they run on a shared data center. You just plug in, like a utility. This makes it fast to get started and it costs less. It's like Gmail compared to Microsoft Exchange. With Gmail, do you need servers and storage? No. Do you need a technical team to keep it up and running? No. Do you have to do upgrades? No. When you use any app that runs in the cloud, you just log in, customize it, and start using it. That's the power of cloud computing. This model is so much better, it's changing the way we think about software. Not just for consumer apps, it's also being used for business apps. We call this enterprise cloud computing. Businesses are running all kinds of apps in the cloud these days, including custom-built apps. Why? Because you can be up and running in a few days, which is unheard of with traditional business software. They cost less because you don't need to pay for all the people, products, and facilities to run them. And it turns out they're more scalable, more secure, and are more reliable than the vast majority of apps out there. Here's why. They're based on an architecture called multi-tenancy. With a multi-tenant app, there isn't a copy of the app for each business that's using it. It's one app that everyone shares. But it's flexible enough for everyone to customize for their specific needs. It's like a giant office building where everyone shares the infrastructure and services, like security, yet each business can customize their own office space. This means apps are elastic. They can scale up to tens of thousands of users or down to only a few. Upgrades are taken care of for you, so your apps get security and performance enhancements and new features automatically. Now, the way you pay for cloud apps is also different. Forget about buying servers and software. When your apps run in the cloud, you don't buy anything at all. It's all rolled up into a predictable monthly subscription, so you only pay for what you use. Finally, cloud apps don't eat up your valuable IT resources, so your CFO will love it. And you can focus on projects that really impact the business, like deploying more apps. Cloud computing is a simple idea, but it can have a huge impact on your bottom line. For more information, go to salesforce.com/cloudcomputing.
In many ways, our memories make us who we are, helping us remember our past, learn and retain skills, and plan for the future. And for the computers that often act as extensions of ourselves, memory plays much the same role. Whether it's a 2-hour movie, a 2-word text file, or the instructions for opening either, everything in a computer's memory takes the form of basic units called bits, or binary digits. Each of these is stored in a memory cell that can switch between two states for two possible values, 0 and 1. Files and programs consist of millions of these bits, all processed in the Central Processing Unit, or CPU, that acts as the computer's brain. And as the number of bits needing to be processed grows exponentially, computer designers face a constant struggle between size, cost, and speed. Like us, computers have short-term memory for immediate tasks and long-term memory for more permanent storage. When you run a program, your operating system allocates area within the short-term memory for performing those instructions. For example, when you press a key in a word processor, the CPU will access one of these locations to retrieve bits of data. It could also modify them or create new ones. The time this takes is known as the memory's latency. And because program instructions must be processed quickly and continuously, all locations within the short-term memory can be accessed in any order, hence the name random access memory. The most common type of RAM is dynamic RAM, or DRAM. There, each memory cell consists of a tiny transistor and a capacitor that store electrical charges, a 0 when there's no charge, or a 1 when charged. Such memory is called dynamic because it only holds charges briefly before they leak away, requiring periodic recharging to retain data. But even its low latency of 100 nanoseconds is too long for modern CPUs. So there's also a small, high-speed internal memory cache made from static RAM. That's usually made up of 6 interlocked transistors, which don't need refreshing. SRAM is the fastest memory in a computer system, but also the most expensive, and takes up 3 times more space than DRAM. But RAM and cache can only hold data as long as they're powered. For data to remain once the device is turned off, it must be transferred into a long-term storage device, which comes in 3 major types. In magnetic storage, which is the cheapest, data is stored as a magnetic pattern on a spinning disk coated with magnetic film. But because the disk must rotate to where the data is located in order to be read, the latency for such drives is 100,000 times slower than that of DRAM. On the other hand, optical-based storage like DVD and Blu-ray also uses spinning disks, but with a reflective coating. Bits are encoded as light and dark spots using a dye that can be read by a laser. While optical storage media are cheap and removable, they have even slower latencies than magnetic storage and lower capacity as well. Finally, the newest and fastest types of long-term storage are solid-state drives, like flash sticks. These have no moving parts, instead using floating gate transistors that store bits by trapping or removing electrical charges within their specially designed internal structures. So how reliable are these billions of bits? We tend to think of computer memory as stable and permanent, but it actually degrades fairly quickly. The heat generated from a device and its environment will eventually demagnetize hard drives, degrade the dye in optical media, and cause charge leakage in floating gates. Solid-state drives also have an additional weakness. Repeatedly writing to floating gate transistors corrodes them, eventually rendering them useless. With data on most current storage media having less than a 10-year life expectancy, scientists are working to exploit the physical properties of materials down to the quantum level in the hopes of making memory devices faster, smaller, and more durable. For now, immortality remains out of reach for humans and computers alike.